So before the class ended, I just wanted to talk briefly about what to expect on the final exam next week. The final exam format will be very similar to the midterm exam. Okay, it will cover the same set of topics of the midterm exam plus everything we've covered in class since then. So midterm exam talked about, from lecture 1, some of the sort of basic concepts. What is operations research? Why do we use it? Why do we learn it? Some of the basic use of Excel, okay, which obviously is probably not going to be covered. Excel functions and things like that won't be on the exam. But why we chose to use Excel, we talked about that. That could be on the exam, okay? And then starting from week 1, we started learning techniques, started learning some of these tools for our operations research bag of tricks, if you will. The first we talked about is data mining. Okay, we specifically talked about 3 algorithms: k-nearest neighbor, multiple linear regression, and classification and regression trees. Okay, we talked about different types of fields, different types of values, numeric versus categorical. And we said when we have an algorithm that's trying to guess or predict or determine a categorical value for records, we call that classification. When we have an algorithm that's trying to guess or predict a numeric value, so compute a numeric value for records, that's called prediction. Okay? Those are just terms we use. They're not always universal in the world, but generally speaking, there are those 2 kinds of data, and some data mining algorithms can be used to do one, say classification, but not the other, say prediction, or vice versa. Some algorithms can be used to do both. Okay, so specifically we talked about how k-nearest neighbor and classification and regression trees can do classification and prediction, whereas multiple linear regression is an inherently mathematical model. It just computes averages and numbers, so it can only do prediction. It can only compute numeric values to predict with. It cannot use categorical data at all. Okay. So that was data mining. We also looked at lift charts and used lift charts and error rates. So average errors or mean squared errors, or I think we use the term root mean squared error to talk about how you can compare 2 data mining algorithms. So which one is predicting or classifying better than the other. Error rates will give you a numerical sense of how off they are, the percentage wrong, or how wrong they were in their prediction on average, and so forth. Lift charts are used to visually describe how much or how differently the algorithm performed versus a sort of random or average guesser. Okay, so for example, if you were trying to predict a numeric value for some records, as a sort of naive or average case, you could just average all the numbers and use that as your prediction every time. So if the average came out to 10, you'd always predict 10, and that's an algorithm. It's not necessarily a good one, but that's the baseline that a lift chart uses. It says, as a base, if you just used average or used a random sort of guess, as it were, based on the data, not random in the sense that you make up the value, but random in the sense that you don't use the data to predict each time. You just aggregate all the data and use a summary, like an average value, to predict every record. A lift chart compares the data mining algorithm, k-nearest neighbors or whatever it is, against that average. Okay, so the further the lift chart, the bigger the distance in the lift chart between the algorithm and the average line, the better the algorithm is doing, if it's above the line. If it's below the line, it's actually doing worse than average, which is unusual but can happen. All right, for particular algorithms in particular cases, they might actually find incorrect patterns or mathematically just work out to predict worse than an average value would. Okay. So that was data mining. The last part of data mining that would be covered is talking about partitioning and why we partition, the problem of overfitting, that is finding a pattern that's not there, or a pattern that isn't indicative of a pattern in all data that you might want to predict or classify, or using some of the randomness of the data and trying to match a pattern to that randomness, in which case that generally leads you to an overfitting situation where you're trying to make too precise or too fine-grained of a prediction or classification based on randomness that you couldn't really account for or shouldn't try to account for, leading you to make worse predictions or classifications. Okay, so the problem of overfitting and how we use partitioning to detect when we have overfit, and thus we can know when we should stop refining and building or revising the algorithm and stop before we overfit by too much. Okay, that's data mining. The next thing we talked about, the next technique, was forecasting. Specifically, we again addressed error rates. We talked about 3 ways to measure error: mean squared error, mean absolute deviation, and mean absolute percentage error. Again, as in the midterm, I don't necessarily need or I won't expect you to memorize the formulas. If I have you compute anything like error on some data on the final, I will give you the formula to use, so you don't necessarily have to remember, say in mean absolute percentage error, that it divides by the actual, not divides by the prediction or something like that. So don't worry about necessarily memorizing exactly how to compute things. I'd rather you focus on why we have those error metrics, and in some cases why one error metric is different than the other. That is, what kinds of errors does one metric emphasize over others. So for example, mean squared error, because it squares the error, emphasizes or places sort of a higher error penalty on larger errors. Whereas mean absolute deviation, it doesn't matter if an error is off by 1 or 3, it's 3 times as worse. When you square it, the difference between an error of 1 and 3 is 9 times, because 1 squared is still 1, but 3 squared is 9. Okay, so mean squared error sort of emphasizes or places more penalty on higher errors, the larger errors, because they get squared. Forecasting models we talked about, we used 4 different algorithms. A moving average model, which is parameterized by how many items you want to average together each time. We talked about exponential smoothing, which uses all the data in the past, but exponentially weights recent data higher than past data. So the further back in the history, the less weight or the less importance that value is given to predict the future. And the only parameter to that model was the alpha, that the fractional value between 0 and 1 you use to weight the recent value versus all past values, or the last prediction. Beyond the exponential smoothing model, we added 2 more facets or 2 more components to make 2 more models. One is to trend. So when your smoothing model will smooth out sort of the jagged or the rough observed values, somewhat like averaging would. However, if those values tend to trend upward or downward overall throughout all time, any kind of moving average or exponential smoothing model will always be behind. That is, they'll always underpredict an increasing trend or overpredict a decreasing trend, because they're only averaging the past and they're not detecting that values are generally trending up or down. So adding a trend to your exponential smoothing model basically just adds in a component that says the difference between the last 2 smoothed values is used to predict whether or not we're trending up or trending down. and that adds another parameter, which is how you smooth the trend prediction, and we called that parameter beta. Beyond that, we also added a component for cycles. When you detect or you know that there is a cycle to the data, values go up and then down with certain periodicity. So every 4 or 10 or 20 or whatever values, the cycle repeats. Then we can use that information to predict the future by saying, what point in the cycle are we at? Do we need to over or under predict based on whether we're at a low or a high point in the cycle? And the cycle component adds 2 more parameters. One is the periodicity, how many items, observed items, you have to see before the cycle is repeated. And another smoothing parameter called gamma, which is used to smooth the cycle prediction itself. So how much weight do you give to recent cycle observation versus historical cycle observation? So that's forecasting. And again, all of those forecasting models used error metrics to compare one to the other. So the lower the error metric, the better the model is doing at predicting. Okay, pretty simple. From there, we move to optimization. We've only talked about linear optimization, so I would never ask you anything beyond linear optimization. There will almost certainly be a linear optimization problem that you will do by hand on the final exam. So you will be given a situation or constraints and things that you will have to graph where there are 2 variables, 2 decision variables, as we call them, and you would have to determine which decision values give the optimal objective. So you'll be given an objective function and asked to either find its maximum or minimum. And you do that by finding the intersection of all the constraints, all pairs of constraints basically, and then which ones form the boundaries of the restricted or constrained solution, X and Y or variable cases, and then which pair of constraints give the optimal objective, highest or lowest, as it may be. Beyond that, so we did linear optimization in Excel, where we could use more than 2 variables easily. We talked about we did a few examples of just generic linear optimization problems like you might do by hand, just with more variables. And then we started looking at very special cases of linear optimization where we had special forms that the solution would take. For example, network optimizations or assignment or transportation models where we used a table where you were looking at rows that represent, say, sources and columns that represent destinations, and you were trying to figure out how much product or information or data or whatever should flow from each source to each destination in order to, say, minimize costs where each source-destination pair has a certain cost or so forth. So those were special kinds of linear optimization problems. On the final exam, you won't be using a computer, so what I would ask you to do in that kind of case is I would describe a problem and I would probably give you a screenshot of Excel with the optimal solution. Okay, so I would give you the solution and then ask you questions about it. That is, what is the amount of data that flows from source A to destination X? Or I would ask, what's the optimal objective function value? Or I'd ask you, like I did on homework assignments, to describe the pattern to the optimal solution. That is, which sources send their data to which destinations, or which sources send no data, or no product, or whatever the pattern might be. Okay, so you would want to just verbally, or written, describe what the solution looks like. Okay. When it comes to network optimization, you can also represent that with a graph with circles and arcs or bubbles and lines or whatever you want to call it, where you could represent, just to give a quick example. So if you had 3 sources and each one had a capacity, say X, Y, and Z, and you had 2 destinations, that each had a requirement, say A and B, okay, then you could visually represent that much information like this. Okay, so remember, you have your source bubbles, you have your destination bubbles. Your sources, what comes into those, it doesn't come from anywhere. It's just representing that source has X available to go out. That is, it can send up to X amount out, cumulative to A and B. This bubble can send out as much as Y to A and or B or some combination thereof. So the optimal solution might theoretically look something like this, where X sends, say, I don't know, I'm just going to have to make up some more letters probably, D to A, and it sends E amount to B, and then maybe Y sends some amount F to A, and Z sends some amount G to B. Okay? So you would want to draw the lines to represent when something is flowing from a source to a destination, and label that line with how much. Okay, you could draw a line from this bubble to this one and label it with 0, although generally I'd say to exclude that. It doesn't add information. If nothing goes on that route, you don't have to draw it. So that's a network optimization problem representation that you can do. So I might ask you on the final exam, given a network optimization problem and the optimal solution taken from Excel, draw this diagram from that optimal solution for me. Right? So visually represent the information given. And then again, I might ask more questions. For linear optimization problems, okay, you have your constraints. Generally speaking, if the value you compute is equal to the constraint boundary, the maximum or the minimum it can be, we call that constraint binding. Okay. Generally, that's how it works. Now, when we came to integer and binary optimization, you couldn't always get exactly to the maximum or minimum value because you had to make sort of decisions that weren't fractional. You couldn't approach it as by little bits. You had to either be all in or all out to select a project. So there you might still have a binding constraint, even though perhaps you're not spending all of your budget, simply because there's nothing else you can do that wouldn't put you over budget at that point. Okay, so I might ask about binding constraints. Given a problem, given the solution, which constraints were binding? And you'd have to explain to me why or which ones were binding. For a linear optimization problem, if you have n decision variables, there will be n binding constraints, right? That is, you have to have you have to have at least n binding constraints to bind or to determine the optimal solution of n decisions. If you had fewer binding constraints, then there's no reason why you couldn't make a better decision, right? Because you'd have some decision variable that hasn't been constrained, that hasn't been limited yet. Okay, so generally speaking, there are n binding constraints. Don't forget, a lot of times there's a constraint that values have to be 0 or bigger, right? They can't be negative. So if I asked you on a problem about a binding constraint and it doesn't look like there's enough binding constraints, remember that some decisions being 0 means they've been bound to not go below 0. So that's their binding constraint, or that's a binding constraint in that case. I don't think I would ask that tricky of a question on the final, by the way, but just trying to give you some review material to think about. So binding constraints, something to ask about. Representing network optimizations, something to think about, and so forth. When it came to binary binary optimization, selecting projects to do from a list of projects, for example, we also talked about some other specialty kinds of constraints like mutually exclusive, at least one of a certain subset, at most one or at most n of something, and so forth. So again, like we talked about on assignment 5 that you're working on, those kinds of constraints come up in binary decision or binary optimization problems. I might find a way to ask something about those, or I might give you a problem and ask you, what kind of constraint is this? Is it mutually exclusive? Is it, what form is it taking? Just to make sure you understand what those kinds of constraints look like. So I wouldn't come out and tell you it's mutually exclusive. I just describe that if you select project 1, you must also select project 2. Or if you select project 3, you can't also select project 4. Something like that, and ask you sort of what kind of constraint or how else could you describe that constraint? It's mutually exclusive or such. Let's see. Anything else about integer or binary optimization? Nothing I can think of. So again, linear optimization, you'll do some problem by hand. You'll generally get a problem and a solution together and asked to represent it or answer questions about the optimality from that problem that I've done. Okay. And then the last thing would be simulation, so something we covered tonight. And again, on the final exam, what I would do is describe a problem. I would solve it in Excel, and then I would give you, say, a screenshot of the probability distribution graph or something, and then ask you questions like, what's the expected objective function value? What's the minimum value? What's the maximum? What's the probability of getting some value or less in the objective? All of that you would have to just read off of the screenshot or the information I gave you out of Excel. Okay, so you won't need Excel. You won't need a computer. All of it will be on paper, like the midterm. And I would give you enough information and then ask you questions about the problem or the solution as it was presented. Okay. Okay. Any questions about final exam? Hopefully that's an apt description of what to expect. Yes? In terms of the length, the final exam will be longer than the midterm. So the midterm, I think I gave you something like an hour and 15 minutes or an hour and 30 minutes to do. The final exam will last 3.5 hours, the class time next week. Certainly I expect people to get done earlier than that. It won't be twice as long as the midterm, but we do have about twice as much material to be covered. So I would expect it to be somewhere near twice as long as the midterm. Okay, about twice as many questions or such. Yeah.
So I guess it's kind of a dumb question, but I don't remember why we exactly chose to use Excel. Was it so we didn't have to write the code?
So why did we choose to use Excel? If you're welcome to go back and look at lecture 1 or the slides, there should be posted. A couple reasons we use Excel. One is it's so flexible. So we used it to do data mining, we used it to do forecasting, optimization, simulation. You can use it for a lot more than that. But it's one tool to use, or one tool to learn to use for many purposes. That's one reason why Excel is so good. There are better tools that do data mining. There are better tools that do optimization and so forth. But that's all they do, right? So it's a trade-off between using a flexible tool that is one tool to solve every kind of problem or many kinds of problem versus specialized tools that you have to learn for each kind of problem. That's one reason we did Excel. It's one thing to learn in this class as opposed to 5 different pieces of software. One of the other main reasons we use Excel is it's so prolifically used in the industry. Just about any job you take has a good chance of involving Excel, assuming you're doing something in operations research or something in data mining or data decision making, something along these lines. Excel almost always comes up as a tool to use. It's just used by so many industries, so many businesses. We could learn other tools in this class, but you might learn a tool that you would never use again in the real world because it's not as popular, or it's too expensive, or whatever. It's not as good in all cases for all kinds of problems. So those are the main reasons we chose to use Excel in this class. It's just prolific use and its flexibility as a great tool for many kinds of problems. And obviously, because of its flexibility and prolific use, there's lots of material on it. I mean, textbooks galore about Excel, right? There's online tutorials on the internet. There's videos you can watch on the internet and so forth, all about Excel. You wouldn't have that vast of a knowledge base for specialized tools necessarily. Yeah.
On assignment number 5, you were saying that you put some wording in there saying turn in Excel as well as any additional materials you create. So for one of the problems, I actually did create a flow diagram while I was thinking through it in my head, and then I just represented everything in Excel.
Okay.
So if you can infer everything that I did from looking at Excel,
when on assignments, when I say turn in the Excel document and any other material, what I mean is any other material that has your answers on it. Okay. Some people like to do the model in Excel and then answer the questions, like what value is the optimal or whatever, in a Word document or something else.
Okay. Right.
I just want to make sure you know you both have to show me you did the work in Excel, built the model, and somewhere I need to see the answers to the questions I asked. If you have intermediate documents, flow diagrams, or things you sketch out, if you think back to Lecture 1, I even suggested sometimes sketch out the Excel model to sort of get an idea of what it might look like first. You don't have to turn that stuff in if it's not asked for in the question or in the problem. But yeah, I just always wanted to see the Excel model that you built and then somewhere the answers. Most people put the answers in the Excel document itself. Some people are pedantic about Excel shouldn't have large forms of text and answers like that. That's what Word is for, or something else, and that's fine. If you want to do it in separate documents, just turn them both in. It's always interesting to me to see who does what and how people organize and think about organization of stuff like that, because not everybody does it the same way. So it's always fun to see different ways people lay things out, formatting techniques, and how people use different programs or document types. Some people have been turning in PDFs, some people turn in Word documents. Probably most people just turn in an Excel document with everything embedded in it. It's probably easier that way, or at least less work.
I thought I was being pedantic to merge my cells and formatting to the left, but I guess I've had code reviews rejected because they went over 80 characters per line, and that violates PEP 80.
Yeah. I am not pedantic about formatting in terms of your assignments and how they look or what they do. Now, there's been a few times when I've wished people would at least format number or dollars as a currency, but it's not something I grade or look for necessarily. Yeah. In the real world, if you're building an Excel sheet that others will use to do their job or you will use later to do your own job, a lot of times you want to put in a little extra work to make it pretty and easy to use for that reason. But for this class, I wanted to focus just on the functionality, learning how to do the problem and learning how to do the solutions for the techniques we were learning. But so I wasn't concerned about formatting and other things. But yeah. Okay. Well, good luck. So assignment 5 due Saturday night. Assignment 6 due next Thursday night. Final exam next Thursday night. So past next Thursday, you'll be done. Right? I'll be grading, but you'll be done. Final grades as computed for the class will be done sometime that following week, early that following week generally. I'll have all grades posted on Blackboard, and you can see your grades there. Blackboard also has, if you've been on it or looked at it, it has your grade for every assignment, midterm, and all that, and the weighted grade according to the weights in the syllabus. So you can kind of get an idea what grade you currently have in the class, if that helps you determine how much work to put into studying and things between this class and others. That's fine. Just one last thing. So final exam next week. obviously, I can't grade the finals as they are turned in. I can't keep up with that anyway, which means the last time, I will see you for the last time next week, but I will still have a paper copy of your final exam. If you're at all interested in getting that back, that's fine. I can arrange to meet you, or we can arrange to have it delivered or left in the office, or whatever makes sense. More often than not, nobody cares, and I end up with a large stack of final exam papers that go to the recycling bin. But just keep that in mind. If you are curious or do want to know what you missed or how you did on the final or anything like that, I can certainly give it back to you. Just not next week. No, not next Thursday. I'll have to grade it first and give it back to you the following week or so.
So we could actually make an appointment come here for that 8th class that they said you could teach if you wanted to.
Yeah. So that 8th week that is after graduation somehow, but was optional, that we are not doing because that didn't make sense to me. I can meet you that next Thursday or any other time really, if you wanted it back, or if you just wanted to see or visit about what you learned or something. Okay. Well, good luck on the final assignments and on the final